Daily, our discussion, this is part 1, of course. We center on linear regression using STATA. So linear regression is widely used and good enough. STATA has enough tools to support any analysis involving linear regression. So some of these tools are what we will examine partly today, and maybe to some extent also in the next class. So for today's presentation, the focus will start by looking at linear regression model specification. It's always good that you start your work by specifying the model, the linear regression model that you really want to run on STATA. Don't just jump into your STATA and start running regression model without you first formulating and specifying the model. So what are the things that you need to specify that you also need to bring into STATA before you can run a linear regression model? We will discuss that under the specification. Then after you specify and the necessary data are provided to STATA, then you can now proceed with the estimation. So we will discuss about linear regression estimation. Estimation is essentially concerned about providing estimates or quantities for the unknown quantities in your model. So the model you will specify will have some unknown constants, and estimation helps you to obtain estimates for those unknown constants. So we will look at various reporting options provided in STATA. And then one major aspect of your specification linear regression model is the constant term. We will look at the various ways that constant term are treated in STATA, or that can be treated in STATA. Then we will look at one particular aspect where you may need to assign weight to variables in your model, to make your estimate fairly accurate. So we will look at situation where you use means as regression variables rather than the actual values or values that are directly observed. So there are occasions when you use average of a particular variable for your regression analysis. Average is subject to a lot of issues. So using them in regression model can distort the kind of estimate you get. So we will discuss about that. And then the last component of our discussion will focus on post-estimation. Precisely, our interest will be on direct influence measure, and then we'll look at some tests for tests for checking assumptions. So we'll be looking at how we can test for violation of the so-called classical assumptions. And the last thing we will consider, hopefully with your cooperation and if time permits, is the effect sizes. So so this is the rundown of our coverage for today. So
sorry, sir, before you continue, I'd like to ask Aisha and Ajaero to switch off their cameras. They are causing distraction. Aisha and Ajaero, please.
Okay, please. So I believe that will be attended to. We'll want to now look at how do we, or what should be our major concern in linear regression model specification. Any model naturally will have terms containing variables and terms containing constant. The other ones might be symbol like equality sign, like plus and so on. So, but basically there will be two sets of quantities: those that are observed, those that are known, and those that are unknown. Those that are known are usually the ones we refer to as the variables. Those that are unknown and that you have to estimate from the ones that are known, they are usually called the parameters. Or the constants in the model. They can only be obtained from those that you have, that you have values for. So in linear regression model, there are two sets of variables that must be known. And a model has two sides, naturally. So you have the left-hand side, and you also have the right-hand side. To be a bit more clearer. So this is a typical model, and on the left-hand side, you have, this is the left-hand side of this equality of this equation. This is the right-hand side of this equation. And as I said, in the model, you will always have two sets of quantities: those that are known and those that are not known. Beta naught, beta 1, beta 2, beta, and so on to beta p, they are unknown quantity, they are constant. So they have to be estimated from the ones that are known. The y is known, which should be known, x's should be known. So the constant, they have to be estimated from the ones that are known. And so the variable, the one that is on the left-hand side is the dependent variable. The ones that are on the right-hand side, they are the independent variable. So before you go to STATA, you must be able to determine, what is your dependent variable. Of course, for a linear regression model, there will always be one variable on the left-hand side. There are other models, simultaneous equation models and multiple equation models, where you could have more than one dependent variable. But for linear single equation regression model, you can only have one dependent variable. And that will be on the left-hand side of your model. On the right-hand side, that's where you have the independent variables. So, but how do you determine what should be your dependent variable? So usually it is the variable of interest. It is the variable that you most often want to study. And it is the variable that you want to monitor. You want to see, look at this diagram. So it is the variable that changes when the independent variable changes. So in some cases, the dependent, or even in all cases, so the dependent variable is actually the effect variable, whereas the independent variables, they cause the change, and so they are the cause variables. So they cause the dependent variable to change. So in mostly your study could be either experimental study or observational study. For instance, if it's experimental study, so your dependent variable is actually the variable the variable of interest to you. The independent variables will be the variables you are manipulating in the experiment. So they are variables that you change, and then dependent variable, they will be the variable you now monitor and see how that manipulated variable or that changed variable or that independent variable, how the change affects the dependent variable. So in linear regression model that we will be concerned about today, the dependent variable must be a continuous variable. Continuous, another way of saying that is that it must be a measured variable, a variable that is measured on ratio scale or interval scale, not variables that are categorical. So maybe the next two lectures we will look at when we have binary dependent variable. But for this linear regression model, it must be measured on the continuous scale. So this technique is not appropriate for dependent variable that is measured on interval, on nominal scale. So now you should be able to make a clear distinction between dependent variable and independent variable. And you must be able to have data for your dependent variable before you go to STATA. Or you must be able to generate your dependent variable, from the existing data. So sometimes your dependent variable could be a derived variable, which means to be a variable you will derive, which is not directly observable, but you have to derive it from existing data. So independent variables, interestingly, there are not so much restriction about the levels, the way it can be. It can be measured, it can be count, which means it can be count data, which means they are discrete data. 10 people, 10 cars, 15 houses, so those are counts. It will also be measured, which means it's on the it's on the interval or ratio scale. Independent variable could be polynomial, it could be linear, quadratic, cubic, could be discrete, binary, or multi-class. So you could have in your dependent variable, you could have x that is raised to power 1, so linear, or x that is raised to power 2, or another term with x raised to power 3. So those are polynomial dependent variables. You could have those that are discrete. Maybe you could have gender, which is having 2 levels. You could have multi-class, which could be maybe color, or which could represent 3 or more categories. So usually those variables, they help to measure impact. The parameters associated with them help to measure their impact on the dependent variable. So I've explained this. So you have the specification mathematically like this, where the dependent variable is expressed as a linear combination of the independent variable x's. So the dependent variable is on the left-hand side. The independent variables are the ones on the right-hand side. They are also called the explanatory variables, and the betas are the ones to be estimated. They are the unknown quantities, but we have to estimate them from the y and the x's that are known. Of course, the epsilon is the error term, which is the population error term. We can obtain the residual when we, after estimating the model. So for purpose of our class discussion, we will start with this very simple model in which MPG, which is mileage rating, we are still using the auto.dta data for now. So we are looking at So we have the dependent variable is mileage rating, MPG, and then the independent variables are the weight and then foreign. Remember, weight is measured on the continuous scale, and then foreign is categorical. You have it's actually binary. You have 1 for foreign and 0 for domestic. So this is our model, and this model is simply regressing the mileage rating on weight and foreign. So you must have these variables in your data before you can be able to obtain in your data set, before you can obtain values for this beta 1 or beta 1 or beta 2. So estimation is basically concerned about finding estimates or quantities for beta 0, for beta 1, and for beta 2. So now we move to the STATA. But before we go on, if there is any question, I would like to entertain 1 or 2. Aisha, please. Okay, there are many types of regression. Yes. How and when do we know how to apply each regression? Yeah. In this instance, may not. So the most common one, and the way to decide which we want to use is to look at the dependent variable. So if the dependent variable is measured on the continuous scale, then you can use the normal linear regression model, which we want to talk about today. If the dependent variable is categorical, let's say binary, 2 levels, then you have to use logistic or other related techniques. So what guides your selection is the nature of the dependent variable. Nation Ngalande, it depends on what you are trying to exactly, I didn't even read it, to achieve. For instance, you may use simple or multiple linear regression if your Y is continuous, while you may use a probability to do. Thank you very much, Ngalande. Any other question? If no, yes. So let's move now to the STATA window. I believe we can see my window. Can somebody please respond if you are able to see the window?
Yes,
You can see it.
Thank you.
yes, Prof.
Yes, you can see it. You can see it.
Okay, thank you very much. So the section that we want to look at today is this menu, statistics. So if you go to statistics, then after summaries, tables, you will see linear models and related. And then you will see linear regression. You will see linear regression. And then, of course, close to that, you will see regression diagnostics. So if you see the way I move my cursor, these are the 2 places that we would like to engage in our lecture today and possibly next week. So most of what we'll be discussing today and next week will be in this particular area. So we are starting with the linear regression. Thereafter, we will look at the diagnostics, and only the first one we will consider today. My colleague will be able to follow up with some of this hopefully tomorrow. And of course, there is also the DF betas for measuring influence. So let's start with the linear regression. But you know already, I've indicated to you that you must have your data before you can even go to your to run any analysis. So presently there is no data. So I will start now with calling for the data we have been using, system use auto. And then, so now we have the data. We can describe the data just to bring on the point again. Then we can see variable name, make, price, MPG, and so on. And going back, the regression model that is of interest to us to start with is the model in which the MPG, the mileage, is regressed on the mileage rating is regressed on the weight, and then the foreign. So we can easily use the regress. This window is called the regress linear regression dialog box, and you can specify the model here. And in specifying the model, you only need to specify what the dependent variable is and what the independent variables are. So you could do that here. Later, we will see how you can treat three ways you can treat the constant. So we will also look at issue of weight. We may not be able to dwell long on this, so we will focus more on the analytic weight. And then we will look at robust estimate, which we will need to use if we are testing hypotheses and some assumptions, particularly when assumptions of homoscedasticity is violated. We will also look at different reporting styles. So let's start with a simple estimation here now. So I want to regress MPG, so I will choose MPG and regress it on, in this case, weight. Look for weight. I've selected weight. I also want to select foreign, so I will select foreign. So if you are going to select more, you can select as many independent variables as you have in your model. So once that is done, I've advised, once you have selected like this, you can come here, copy the command, just click copy and come to command so that you don't work from that dialog box. So you can just copy that command and paste in the command window so that subsequently you can be able to, you can save that command and you don't have to go back again, click linear, click this, and so now we can run. This is the regression of MPG on weight and foreign. And as I said, the whole essence of running the regression is to obtain estimate for the unknown constant. So this is the intercept, the constant. This is the beta 1. This is the estimate for the beta 2. So you can see those estimates in this under the coefficient. And of course, we know that this class is not basically about statistics, but we cannot run away from discussing a bit of it. So the first part that you see here, let me say from this part, is what we call the analysis of variance. And you did that last week, where the total variation in the MPG is partitioned into two. Variation that the model is able to account for, and the variation that the model is unable to account for, which is the residual. So the total variation is this, and the model is able to account for this, and this is what the model is not able to account for. And this is the degree of freedom, because we have three parameters there, so that is the 3 minus 1, and there are, of course, 74 observations, so you have to remove the number of parameters from the total number of observations. That gives you this degree of freedom. For the total, it will have to be the 74 minus 1. And here, that is the mean square error, which is simply the average, the SS, the sum of square divided by the degree of freedom. Same with the residual here. This is the mean square, the mean square error is 11 point this, and the square root of the mean square error is what you have here. So this is the F statistic. This is the p-value, which is 0. The F statistics helps you to test for the joint significance of the independent variables. To what extent does the two variables jointly influence the dependent variable? So since this p-value is very small, very close to 0, this is rejecting the null hypothesis that they don't influence the MPG jointly. So we now conclude by accepting the fact that they have joint influence on the MPG. So the R square again helps you to measure the joint contribution of the two independent variables. So we can say now that about 66% of the variation in MPG is accounted for by weight and falling. This is adjusted R square, which is going to make sense if we are comparing two or more specifications with different sample size and different number of independent variables. So when you have to select among competing models, preferably you use the adjusted R square. R square should not be used because it's not going to it can continue to increase even when you are adding nuisance variables to your model. But below here you have more detailed information about their individual. So whatever you see here is providing information, collective information about the model, whereas the information you have here is about the individual independent variable. So you have the coefficient, you have the standard error of that coefficient, you have the t, which is the coefficient divided by the standard error, and then you have the p value, which helps to decide whether weight is significant or not. And in this case, weight is significant, so you reject the null hypothesis, and then you can have the confidence interval. As a matter of fact, one thing you should always look out for this. In another, I've had to give a lecture on how we normally abuse the p-value. P-value is not the only way for taking decisions in regression, particularly. You could base your decision on the confidence interval. And once your confidence interval accommodates 0, then that variable is not significant. So that variable is not important. So that is the result. Now we can look at if this report that we have seen now is based on choosing significance level to be 95. Let me show you the window again. So the default level of significance is confidence. The default level of confidence is 95. So if you must, of course, you are allowed to use any other confidence level. But if you don't, if the default one is 95 and you don't have to state it in your command. But if you must use any other one, you have to state it. Let me say, for instance, I want to use 90. Then if I copy, this will be the new command. So this will be the new command. So I need to now include the option level 90. But look at the previous command. I did not include the level. So if the level is not included, if that option level is not included, then it will report the confidence level to be 95%. So that's the difference. So this is, of course, you will see it here, just as you will notice 95 here. When I change to 90, you also have this. So this is the 90% confidence interval for the coefficient. We could also, of course, change if we are interested to a more stricter level, 99. So we can also change as long as it's not 95. If it's any other thing, we have to include that option. Now let's go back to here. We are still talking about reporting. So I may be interested in the standardized beta coefficient. The standardized beta coefficient, which is which allows you to, okay, before I even go to that, if you look at the p-value only talk about the significance, actually. It doesn't talk about the importance or the relative importance of the coefficient. It talks only about whether that coefficient is significant or not. But beta coefficient, which is a normalized coefficient, which is normalized using the ratio of the standard deviation of the dependent variable against the independent variable. So the standardized beta coefficient will be preferred. So let me use the standardized beta coefficient and still use the 95% confidence level. So if I want that, then this is what I get. So I can run this. So one thing you have now noticed is that unlike before where you have result for confidence interval, once you use the beta option, the confidence interval is removed and you have result for the beta coefficient. So in terms of absolute value of the beta, you will see that this coefficient weight has is more important compared to foreign. But if you are using the value here to judge, you will definitely be wrong. So in terms of choosing variable that have are interested in variables that are more relatively more important, in explaining the dependent variable, it's better you use. It's preferable to use the better standardized the beta coefficient. So what else? You can also go back and then you may choose to say, okay, I still want 95%, and but I don't want standardized, but I want to suppress the confidence interval. Sometimes you can say, I want to suppress the confidence interval. So you check on this. Let me copy that command and paste there. So you will see this option, no CI, is simply saying no confidence interval. I'm not interested in that. Don't report that. So so you can see the output have done away with the confidence interval. All I need to include in the command is no confidence interval. Then no CI, sorry. I could also say, okay, I want to suppress p-values and test statistics. So let me copy this and then put here. So what I'm saying is that I don't want to see p-values in my other statistics. So p-values have been suppressed, but I have confidence interval, and I could possibly still make I could still interpret or make my decisions based on the confidence interval. Maybe one more thing we can do now. I may want to look at the MPG here. I may want to give it a name directly, in my output. So if I want to report, give a name to that, I will type in this space the name I want to give it. So I can call it mileage. I can call it mileage. So let me record this. And then let me copy this. So this is how to write the command. And if I run this now, you will see, unlike before, where you simply have the variable name MPG, it has been given a new name, a substituted name, mileage. So easily you can see that mileage is the dependent variable, and these are the independent variables. I think the last thing we would like to look at is another option. Maybe if I don't want header, so I can say no header, no header. So so I could easily come here and simply say no header option. Put no header option. So with no header option, it means you have instructed STATA to do away with the ANOVA component of the output. So it has removed, we only have output on the coefficients, the standard error of the coefficients, the T, the P, and so on. But the ANOVA part has been removed from this analysis. Great. Any question on this? This is all about different ways of reporting the output of your model. Am I alone?
No, Prof, we're with you.
We're with you, sir.
So far, so good. Or any
Please
question?
continue, Professor. We'll get you.
We're with you, sir.
Okay.
The thing is touching us, sir.
Okay, that's good. Somebody said, could you please explain when truncated regression is used? Yes, when we get to that, we will talk about truncated regression. Don't let us truncate now. Let's even use, don't let us truncate, right? How is it different from 2-bit? Yes. How is it different from 2-bit or pro-bit 1 and 2? I've told you that the one we are doing now is not for 2-bit nor pro-bit. We are doing linear regression model in which the dependent variable is measured on a continuous scale, and you don't use 2-bit or pro-bit for this kind of model. So I don't get you well, Professor, about the standardized beta coefficient. Yes, I said the p-value will help you to decide whether the independent variable is significant or not significant, but they don't really tell about the relative importance of the variables, of the independent variables. So the beta coefficient, which is a normalized coefficient, gives a better criteria for judging which independent variable is more important, in the model. But the p-value does not play that role. Most people often use p-value to say their variable is important. No, it only shows that the variable is significant. It doesn't really show relative importance. In other words, it only shows that your model, as far as the model is concerned, that independent variable should be included in the model and should not be excluded. So, or is needed to account for the variation in the dependent variable. Prof, what is the implication having a high or low MSE in a model? Of course, the most important in regression model for judging or the predictive performance of your model is either the R-square, which is also used to compute the F statistics. So you can use the F statistics, the R-square as the basis for assessing. You know that MSE is also used to compute your R-square, if you know that. So if rather than using MSE alone, you could simply use the R-square, which takes into consideration the total variation, not just the MSE alone. So it's better to use the R-square. But I've also told you that if you are to choose between competing models, maybe you have model 1 having 2 independent variables. You have another model having the same 2 independent variables and another one making 3. And you now want to choose one from these competing models. You can use adjusted R-square for that kind of to make your choice. Right? So if there is no other question, then let's move to the next. The next aspect is the aspect of how we normally treat the constant term. So look at this model here. So I'm interested in regressing weight on the length of a car. So if I believe that a car that is having 0 weight, of course, or a car with 0 length should have no weight at all. In other words, if the length here is 0, then I don't expect to have weight. If I put length to be equal to 0 here, then everything here will be 0. And of course, there will still be weight, which will be equal to beta naught. So this kind of model may not be, the beta naught will not have any. So the appropriate model will be this one. And in this case, the moment length is equal to 0, then weight will automatically be 0. So what has happened is that in this case, beta naught has been suppressed. So this is what we mean when we say the constant is suppressed. So there are 3 ways by which the constant, beta naught, can be handled in STATA. And one way is to leave it. And in that case, you don't even need to check anything here. So it means the constant can be there. In most models, it's even advisable to leave it, to leave the model because to leave the constant, even though it may really, you don't need to interpret it. So it's just like the one we did here. So most cases, the constant may not have any logical interpretation, but you may also, the only thing, if you remove it, it has implications, lot of implications, particularly on all the tests. But it's too, we can't have time to provide all the details here. So let's look at what happens if we decide to run the first regression. So if I have, let's go back to this, and I want to regress weight on length. So I'll choose length here. So this is length. So I have this. Let me be sure that. So at 95%. So copy this. So this is regression of this. So in this case, you will see that we have constant, and we have not suppressed the constant. But it will be difficult to interpret this constant. It only means that if the length is equals to, zero, as we have seen here, if the length is equals to 0, then the weight of the car will simply be negative, as you see. And no car weights. So it will be difficult to interpret this. And that's why some researchers would prefer to suppress the constant. So if we now choose the option of suppressing the constant, so we will come here and say suppress the constant term. I can suppress that. So I'm still having it. So I will use the option no constant, to be able to suppress the constant. So if I run this regression now, of course, I still have my ANOVA, but you can see the constant term has been suppressed. So it's easy for one to now interpret that. So in this model now, you have the beta one to be 16.29829. So which means for every unit increase in the weight increased by 16.26, whether tons or whatever, for every unit increase in the length of the car. So weight increases by this amount. That's what it means. And this makes sense to say if the car has no weight, then has no length, the weight is negative. It's not very realistic. So that's one. That's the second way of treating constant. Sometimes also you could have a user supplied constant. So in this case, user supply constant means the researcher has a constant that is going to be used. So if that exists, you could possibly use this model. Let me give example. Suppose we have just a typical situation where we might need to use no constant. Let's say I use this previous command, and so I will say regress weight, length, and then say I will use this bn foreign. Now and say has tons. As tons simply means, if you recall that variable foreign in our data actually has two categories. If I show you the data, foreign has two categories. So it's a binary variables somehow. So it's either domestic or foreign. So that variable is either domestic or foreign. In the previous regressions that we have run, maybe I should repeat that. Let me just say, copy this just to make the point a bit clearer. If I run this, and in essence, I run regression of weight on length and foreign, then I have this result. What this means is that there is only one constant to this model, and that constant is minus 2850.25. Now let me run this, and I say this model has constant. Now, what do we notice is that I have ensured that each factor has its own constant. In other words, you have a model now in which there are separate constant for domestic and separate constant for foreign. So this expression forces STATA to ensure that each factor variable has its own constant, rather than a common constant that you have here. So it's now possible to specify within here. Now you have a model that will be weight, that will specify weight as a function of length and domestic. So the constant will be for domestic. Or the second one will be a model that specifies weight as a function of the length and the foreign. And this will be the constant for the foreign. So sometimes you use the second, this one has constant option. So if you specify this, it shows that you have constant, and you could now you will see that in this one, because there is no factor variable, as you can see, the STATA tells you that has cons is false. So nothing has really changed if you compare to what we have previously. So because there is no factor variable, there is no splitting of the constant. So this is an advanced option, total sum of square. Let me. So this is an advanced option which total sum of square with constant. So if you want to specify that, you have this. So in this case, the total sum of square, you can see, is very large. I think for now, I would rather advise for earlier this not to use this one, because it will really confuse you at this point. It's not one that you should go for. But for now, you can justify why you want to suppress your constant, or why you don't want to suppress your constant. So I will encourage you to play around these two options for now. Where you have total sum of square with constant, that's where you use a different mean for computing the total sum of square, and it's not one that I will advise you to use at present. You won't be able to explain that. So limit yourself to suppress constant, and if you have factor variable that you want to compute different constants for, them, you can also use the second option. So that's that.
I have a question.
Yeah, please go on.
I have a question, Prof. Thank you for your lecture.
Yeah.
Yes, my question is that place that you said no constant. Or okay,
No
has constant. No, the place you said that it will have constant. So when I looked at the result, I was seeing coefficient Is it the same thing as constant?
Coefficient, okay. Okay. I think I understand what you are saying. You are referring to this place, right?
Yes, that has constant.
You know, so parameters in the model, they are commonly called the like here. So we call those unknown quantity, we call them constants. But ideally, this beta naught, even though it's also a constant, STATA is the only one that STATA calls constant. Is that okay?
Yes.
So it's the only one that STATA calls constant. Any other one which is attached to a variable, STATA calls them coefficients.
Coefficients. Yes.
Is that clear?
Okay.
So
clear.
STATA only generally you will regard them as constants, but STATA makes distinction between constant and coefficients.
Coefficient.
So
Okay.
this beta naught, STATA sees it only as the constant in the model,
Constant. Mhm.
but actually it is the intercept. Any other one, they are STATA sees it as coefficient. Do I answer your question now?
Yes, Prof.
Great. Any other good question? What does it by? I think I've explained what it means by suppressing the constant. By suppressing the constant, of course, in the beta coefficient you won't have constant. You won't have constant because it's standardized, so you won't have constant. Prof, the result of the suppressed constant is improved relative to that with constant. Why is this so? Why you advise the use of suppressed constant for better result? I'm not saying I'm advising you. Please don't. I put a caveat. I'm talking in terms of interpretation. Statistically, it is not the best advice to suppress constant because it will affect the value of your even R square, F statistics, and so on will be affected. And I don't want to go into those details. So it will invalidate your inference. Let me put it that way. Once you suppress constant, you can only include constant and refuse to interpret it. No, don't bother yourself to say you want to interpret the constant because its interpretation will not make any, in most cases, it will not make sense. So, but there are situations where you are more concerned about the, you want to concerned about making your result to be a bit more realistic in terms of the way you interpret it. You know, so that is it's a very dicey thing, but you have to know what you are doing before you choose to suppress or not to suppress. So let's move on now to our time is really moving fast. So the other aspect which I want us to talk about is the aspect of the standard error robust estimate. Different approaches to in estimating linear regression model. We use the ordinary least square, which is
sorry, Prof. I want to really understand something.
You want to take me back? Our time is moving.
Sorry, Prof. In this case, when we regress weight and length, I will have constant. I think from what I can explain is that the meaning of the constant is the weight is a dependent variable. The value of the weight when length is 0. Is it? Sorry, Prof. I just want to understand.
I'm not sure I got you. Quickly, can you repeat your question?
I said in this case that we regressed length over weight.
Weight on length.
Weight on length, yes. I now said since the weight is the dependent variable, that if we have constant, the value of the constant means the value of weight when length is 0.
Exactly. Clap for yourself.
It's okay, Prof. Thank you.
And then what will be your weight when your height is 0? So this is the challenge. You know, model is supposed to be an approximation of the reality, not necessarily. There is no model that will capture the reality exactly. But sometimes you want to have a model that you can easily interpret. You also want to make your model as simple as possible, or to at least reflect the reality, you know. So there will be trade-off here and there. You must get used to that. If you retain the constant, you must be able to avoid the temptation of trying to interpret it. Because if you interpret it and you say the weight is negative when the length is 0, people will take you up. Your result will not be speaking to reality. So that's the point. But if you have a model that simply suppresses the intercept and you are able to relate the weight with the length, that makes sense. And if you say when the length is 0, the weight is 0, people get along with you.
Yes, sir. Hello, sir.
Yes, Victoria, go on.
Sorry, sir. I want to ask the question where you say weight as function of length and domestic. I don't really understand it.
No, I was trying to create a scenario where you will need to use the option no constant, so that each factor, each category in the factor variable will have its own constant.
Okay, sir.
If you listen to the lecture all over again, you will be able to understand. So let's move on now because of our time. Now, let's look at another situation, and that's about finding robust standard error. And I was trying to say that in this situation, you know, you possibly may be interested. I was saying that regression model, you use the ordinary least square technique to find the estimate. But the ordinary least square method has a number of underlying assumptions. And one of them is the assumption of constant variance. And the moment this assumption fails, then the standard error will not, your inference will be invalid. And your inference about whether it's significant, whether you are using the t-test or you are using the f-test will no longer be valid. So there are different ways to overcome that and make your inference valid. And that is by using the so-called standard error stroke robust statistics. So there are robust statistics. Some of them also, if you are sure that the variance is constant, then you can use this. Of course, is the default one. So all the results we have obtained so far in this lecture today, they are from ordinary OLS. So we obtain those under the assumption that the variances are constant. But when they are not, we might need to adjust and use robust statistics. These are options for bias correction. You can also use. So let's quickly run a few of them. Some of them are also based on computationally intensive techniques like bootstrapping and jackknifing. So I can't give you more stories about all this, but they are options. The one I will recommend you to learn to use is the robust option. So let's say we are interested in a model. Let me. So first of all, just for purpose of explanation, suppose we are looking at energy efficiency of the cars. In that case, we might need to generate a new variable. Let me, for the dependent variable, you know the original variable is MPG. But if you are now interested in not mileage rating, but you are now interested in energy efficiency, for instance, I can say generate. We have discussed generate command, which helps you to generate a new variable. I will call it PMW equals to, now I'm looking at just the relative efficiency measured as 1 divided by MPG divided by weight, and then multiply by 100 times 1000. What this one is simply trying to calculate is a new dependent variable named GPMW, which is looking at the relative efficiency of the cars in the data set. And this relative efficiency measures how much it takes a car of maybe a 1,000 weight to cover maybe 100 kilometers. So that has been measured, and then we can even summarize that new quantity that we have this. So this is the summary. There are 74. This is the average efficiency of the 74 cars. This is the minimum. This is the maximum, which means that for the cars in the data set, 74 cars in the data set, the relative efficiency lies between 1.09 and 2.30, something like that. And of course, we can now run our regression and simply say regress. So we don't need, you can now be using command. I can say regress the new variable on foreign, for instance. Let me regress the new. So I want to regress relative efficiency on foreign. Remember, foreign is a factor variable. You have foreign and domestic. So here you have the results. So and you can see that the relative efficiency, the estimate lies 95% confidence interval lies between 0.13 and 0.36. And of course, it's very the nature of the car, whether foreign or domestic, has significant impact on the relative efficiency. Now, why are we doing this? We believe that variability, the variance of domestic cars might not be the same as the variance of the domestic cars. So in this case, the standard error which the reported here, the standard error that is reported there, obviously will not be appropriate. So should there be any, should the constant, the variance not be constant across the two categories? So we might now want to include an option, VCE. So that is the variance covariance matrix, and then we use the option robust. What I've done here, you could easily go to here, come here, select the new variable GMP, select the independent variable rather, which is foreign, and then stop that, and then come to robust here and select robust. Of course, you could choose any of these three bias, any of these three methods for correcting bias. Where you have some comments here, this is best for homoscedasticity, this is best also for homoscedasticity. So this is the default. So if I copy this, I just copy this and paste. So that is the command. So you can generate the command from the dialog box as I've been doing, and you simply paste. So look at the new result. What we notice immediately is that the result, the ANOVA aspect has been suppressed. So the moment you use the robust standard error, it's not going to give you, because the ANOVA one is produced from the OLS technique. So now you have this. Of course, nothing much, but the interval has been widened. The interval, even though it still has 95%, you will see that the interval, no, it's, yeah, the interval seems to have been slightly widened. So that is, this one now is considered to be the robust standard error. This one is considered as the OLS standard error. That is the difference between these two. Then, of course, if you want, for instance, if I want the one for H1, I can take this one, and then let me copy this, put it there. So this is actually H2. So I can run this. So this is robust standard heteroscedasticity consistent, no, to this is the standard error from that. If I want this one, that is, I think, H3. So I can copy and paste. The reality is that it has not changed the decision whether we are, but it's only good that you do that, because there are instances it will change, you know, it will change the decision. Is anybody trying to come in? So we could also use we could compute the standard error from using either the bootstrap approach. So we could simply use the bootstrap. Don't let us, you could select any options or options there, but if you are versatile with what you are doing, you can. But you could simply put bootstrap for the default options, to use the default options for the bootstrapping. So you will see how the bootstrapping is done. I'm sure most of you know what bootstrapping is all about. So this is the bootstrap standard error. You could also have your standard error from the jackknife technique. So you simply select the jackknife and then you copy and paste. So again, you see the result. So this is how we will say about robust standard errors. All you just need to do is to come to this site and choose. It's very important, because if you use the OLS, the standard error from OLS, when you have a problem of when the no constant assumption is violated, it will render your inference invalid. So, but any of these technique will make your inference to be robust and realistic. So, any question before we move on to, we're almost
yes, sir.
Yeah.
I have a question,
No
sir.
question. Please go on.
Yes, I have a question, sir. Yes, sir. Can I refer
on.
to OLS as regress GMP foreign VC? Can I refer to OLS as that?
To what? OLS as what?
So, as regress GPMW foreign VCE HC3.
Do you mean if, okay, is this what you are saying?
Yes, yes, sir. Yes, sir.
Ask your question now.
No, I'm saying that can I refer to OLS as this?
As
or is there difference between OLS as this? Yes, sir.
This one now, if I run this regression.
Yes, sir.
This is OLS results. So the
Okay,
standard
sir.
error, the standard error I obtained here is the standard error from the OLS.
Okay, sir. Okay, sir.
So what I'm saying now is that, we are regressing the relative efficiency of the cars on foreign. But
yes, sir.
if you have a situation where, foreign has two levels.
Yes,
foreign
sir.
has cars that are foreign cars and cars that are domestic cars. Now,
yes, sir.
assumption is that the variance are the variances are the same. So the variance of domestic is the same as the variance of the variance of the foreign. So if you assume that, and that assumption
Yes,
is
sir.
not tested and it's not checked, of course, so OLS assumes that the variances are equal, they are the same. But
Okay, sir.
when the variances are not the same, the result you have here will be invalid.
Okay, sir.
You cannot conduct inference on those results, particularly your p-value, for instance, your f, your t statistics, they are no longer valid once the assumption of constant variance is violated. So a way out of that is to use the robust standard error. And we have looked at different robust standard error that you can use. I think you follow. You can use the HC2, robust HC2. You could use robust HC3. You could use robust jackknife standard error. And the last one was the bootstrap standard error. So these are different ways of overcoming the challenge of no constant variance. Is that okay?
Prof, sir, I have a question.
Go on, but be mindful, our time is running.
Sorry, I won't waste time. I have asked earlier in one of our earlier classes that what is the significance of R squared? You said when we get to regression, you will explain. Because I can see the significance of the R squared value and the adjusted R squared.
I think I've explained it today. I told you that R squared simply gives you, is a measure, we call it coefficient of determination. And it simply tells you the proportion of the total variation in the dependent variable that the independent variables explain or co-explain.
Yes, sir. Yes,
is that okay?
I understand that. But can we adjust R squared of 21%? Can we adjust it as being adequate, sir? That's my problem.
Okay, there is no threshold. There is no threshold for
there is
no threshold for R square. R square is not R square has no threshold. So what makes R square to be meaningful or senseless is this p-value, because once you look at the p-value for the statistics, look at it, is very significant. So if it's significant, is already saying that those independent variables jointly explain the dependent variable. So take your decision on the basis of that. I've also told you that the adjusted R square is useful only when you have two or more competing models. Maybe you have model 1 with 2 independent variables, another model 3 independent variable, another one 4 independent variables, and all of them have the same dependent variables, but the number of independent variables are different, and you now want to choose one among them, the one with highest predictive power. Then use adjusted R square as the basis for your selection, not R square.
So that means we consider the one with the highest value of adjusted R squared.
Plan for yourself.
Thank you, Prof.
Great. So let's move on now to the next aspect of our discussion, which is the issue of using means as so I'm going to use a data set that is completely available. I think it's available online. So that data set is available online. So you will need to copy that link. You will need to copy this link from the PowerPoint, from the slide. So, and you need to have internet for you to be able to get the data from the internet. Now you could look at the data. Just look at the scribe. So in the data you have this variable state, state 2. State 2 means 2-letter, means death rate. POP means population. Mid-age means median age. And of course, region means census region. Now, our real concern here is that if state in US. This is a 2-letter abbreviation. This is the death rate for each state. This is the population for each state. This is the age of people in the state, and this is the region. Now you know that median is a measure of average. So suppose, and of course, you can't get an average. Average utilizes information from the entire population. So this average now is taking into consideration everybody in this population, everybody. But certainly, this. So if I'm going to regress, if I want to believe, let's assume for purpose of analysis that death rate is a function of age. So if you have more aged people in the population, then you might expect the death rate to be high. But the age that you have here is not age of individual. Specify the death rate here as the dependent variable, and then we specify the median age as the independent variable. So the point we are making is that because this median age is not observed on individual, it's observed on the state, and is taken from the population of the state, and of course the states, they have different populations. Population size varies from state to state. So if you run the regression without attaching weight, you are giving equal weight to all the. You are treating each state as if they are the same, and that's where weight comes in. So we use analytic weight because we are dealing with average. I was also talking about importance weight. So using the household consumption, for instance, that a household may attach importance to bread. The importance attached to bread might be different from the level of the importance attached to some other household consumables. Let's even say sugar. So here we are choosing analytic, and then we select the variable population as the weight. So you can just copy that and paste there. And then, of course, sorry, we don't need this. Came up because I've not removed this from. So I can run this regression now. So this is the weighted regression, and you will see in our results, you can see the sum of the weight, which is actually the population of the total population for the country. And then this is the sum of square, and weighted regression. We can also use frequency weight. If we use another weight, so take for instance, if we use the F weight, in which case we are assuming that the population have we are using Z, because each country appear once. So we are giving the same this thing. You can see not there's really the confidence interval is different, and that's even why we are doing this. You can see that the coefficients are the same. Look at it. So where we use the frequency weight, that is F weight, you can see the coefficients are the same. The standard error differ. Of course, you can see a lot of the magnitude of the results in the ANOVA is quite huge. So this is not appropriate. That's the point I want to make. But this is more appropriate for our analysis. So two things that we want to establish here. One is the fact that you might need to run regression on summary statistics, not on the unit statistics. And if you are going to run regression on summary statistics, then there will be need for you to use weighted regression. So that's the point. You might also, in other regressions, if you are doing maybe econometric analysis, household and so on, you will also need to learn about weight. I can't discuss all of that here. And that's why you will see sampling weight, particularly if you are doing survey studies, you might need to have sampling weight, and so on and so forth. So this is where you come when you have to use weight in your regression. Now, maybe we are almost oh wow, we'll spend a little extra time today. The next thing before the last is the issue of what do you call it? The issue of direct influence. The DF beta influence. So I'm going to use the data we have been using. So let's use the auto system use auto data clear. So I'm back with our auto data, and if you come here, I told you when we started that we will discuss here, and this is where we have been discussing so far. We've talked about weight, standard error, reporting. So we seem to have covered most issues around here. Then, if you recall, also I said we will talk about this one, specification test, and DF beta. So DF beta is used to measure how much impact each observation has on a particular predictor. So if you are interested in how observations, outlier, I think last lecture or so, my colleague was talking about outliers and how outliers could influence. So there are observations that are influential. So one way of measuring the influence of observations on our result is to calculate the DF beta listing. So how do we do that? Let's before we do that, let's of price. Let's say we want to regress price of automobile on the weight, maybe on the weight of the automobile, on the mileage, the mileage of the automobile. So excellent. So this is the analysis. This is the results, and here we could see that mileage actually has a negative relationship with price. Weight has weight has a positive concern. Our concern is to analyze which to look at influential observation in our data. So we could possibly go to let me see. We could just go to statistics, linear models, and related, and then go to regression, diagnostics, and look at the BF beta. So if we can select all the variables in the model, weight is a variable there, MPG is a variable there. So this is what we call this one of the post estimation outputs that we can produce. So after we have run the regression, so this result will still be obtained based on this regression. So I can simply copy this and paste here and say BF beta weight MPG. So it tells you, and if you look at the variable window, it has created two variables, DF beta 1, DF beta 2. The two variables are there. In fact, even if you don't state the variables and you simply type DF beta, once you don't mention any variable, it will on its own utilize all the independent variables in the model. So it will still produce the same thing. So, but it's including DF beta 3, DF beta 4 because 1 and 2 are already there. So I'm going to drop the 4 of them and then recompute them just for purpose of explanation. So I will simply say DF beta. So I now have DF beta 1, which is DF beta for weight. I have DF beta 2, which is DF beta for MPG. You will see that I could obtain the two of them even without beta command. So at this point, I can sort this data because I'm interested in the variable that the observations that are influential. So let me sort based on weight and then make of the car. So I've done that. Then let me list. Just for our discussion, let's list make. I list make. I list the price. I will also list the weight, the DF beta weight, DF beta weight. Maybe before that, let me list weight. Okay, so I list DF beta weight only if the absolute value of DF beta weight, only if the absolute value of DF beta weight is greater than any value that is the threshold, any value that is greater than 2 divided by the square root of the number of observations. In our case, the number of observations is 74. Then all those observations that are above that will be listed. Let me use divider. Divider allows you to use line to separate the quantity. So here you will see that the ones the top among the list is VW diesel. Lead the pack of those observations that are influential. Precisely observation 9, 33, 51, 71, 73 are the ones you have to watch out for. that will influence the coefficient or the coefficient estimate that you have here. So this is the essence of DF beta. It helps you to detect variables, or sorry, observations that are influential. Not variables per se, but rather observations that are influential, that will affect or change the coefficient values very seriously. Then let's also look at yeah, that's if we use this one we have done now, we have looked at the DF beta 1. Let's look for DF beta 2. Let's look for DF beta 2. I'll just change this to 2. So everything remains. So even with DF beta 2, I can see observation 9 is also there. 33, 51 is not in the DF beta 2, but I can see 71 is in both. 51 also is in both. But one that is missing here, I think, is 73. 73 is here, but it's not here. So in essence, DF beta helps you to detect observations that are influential. In other words, those observations that can impact on the coefficient of your regression. So you may need to watch out for them. And then in some cases, you might need to watch out for those for those observations and decide how to handle them. So finally, the last slide I have is it the last one? Yes. It's about measuring. No, not. We still have many slides, but I will run through them quickly. And you can also, I won't waste time running them, but I will explain them so that you will be able to understand. The aspect on regression diagnostic, I've talked about DF beta. I've also, this is where we need to talk. And this, you have a number of post-estimation analysis that you can carry out. Test of heteroscedasticity, you can obtain your information matrix, you can do Ramsey regression specification test, and so on. So you can do all of that in this window. So let me say I want this. I can just copy the heteroscedasticity test. I can copy and then run. So this is Westbar test for heteroscedasticity. Obviously, you reject the null hypothesis. So the test. Hello. Yes.
We have missed the major part of the explanation. We're not hearing you.
Oh, we are at what point?
Please, sir, majorly on the interpretation of the results.
Okay. So I was saying that this is a Bruce Pagan Cook Wisbach test for heteroscedasticity. This is the null hypothesis. The null hypothesis says that the variances are the same, constant. And going by the chi-square test, statistics, the p-value is very, very small, far less than 0.05. Therefore, you reject your null hypothesis. So the residual exhibit heteroscedasticity. So in which case, variances are not constant. Variances are not constant. So that is this. You could also come again, check for, there are several things. Look at the variance inflation factor, for instance, which helps you to check for multiple and so this is variance inflation factor, which helps you to check whether you have a problem of multicollinearity. You could base your decision based on the individual or the mean. Different opinions. Some will say if this one is above 10, then there is a multicollinearity. Some will even say 5. So there is really no, but from what is here is quite small, so one can say there is really no problem of multicollinearity. It will also be based on the reciprocal of the VIV. So your decision could be based on the VIV or the inverse of the VIV. So there are other, of course, there are other tests that you can carry out for you could even variance matrix. So this is the variance of weight. This is the covariance of weight and MPG. This is not the variance of the residual, of course. So this is the covariance of the residual of weight and MPG and so on like that. So the last thing I would like to talk about is the effect. Of course, again here you could look for effect size. I think it's yeah, you see effect sizes here. Effect sizes, you could even just copy that, and then this is the last one I will talk about, and then we close. So we have effect size. This is a measure of effect size. Generally, there are two types of effect size you could have. There is the eta one. If you look at so the default one is the eta that you see that is reported here. You could also have the omega effect size. So the omega effect size. Now, in interpreting your result, information about whether your variable is significant.
Sorry, Prof, you went mute again. You went mute again, Prof. Went mute again.
Oh,
said
no, I was saying that. Yeah, I said in interpreting your model or your result, you could p-value will only tell you whether your variable is significant or not. So there is a difference between statistical significance and practical significance. In linear regression model, effect size helps you to analyze the practical significance of your model. So you will see from eta squared, you could know the practical significance of your model as well as the practical significance of your weight and of the predictor variables. The same thing for the omega. So p-values, whether from the F, helps you to know, to determine statistical significance. But you all know that, or you will agree with me that statistical significance is is of less concern than the practical significance. So effect size actually measures the practical significance. And of course, we don't have luxury of time, which we'll have discussed. And as I knew that, look at this, the last slide, good enough. There is a link there which gives you access to this article, and I will encourage you to read the article. So even though these are 4 different scenarios, which helps you to interpret effect size. If your sample size is very small and your statistical significant outcome is not significant, but the effect size is large, the interpretation is that your your conclusion is not reliable. In fact, it has low statistical power, and chances of committing type 2 error is very high. Type 2 error is when you accept a wrong hypothesis, right? If the sample size, if you have used appropriate sample size, and the statistical significant result, you are able to establish significance, you are able to establish significance, and the effect size is large. This is reliable. This is reliable. So effect size is very important, and it goes alongside the sample size. If the sample size is appropriate, and you could not establish statistical significance, and the effect size is small, yeah, your conclusion is still reliable. However, if you have very large sample, now that we talk of big data, and it's significant because large sample also could induce significance, seriously. But if the effect size is small, the result is not reliable. Even though the statistical power is very high, but you are likely to commit type 1 error. This is the finding, summary of the finding from this paper, and I will want you to find time to download the paper and read further. Thank you very much. I've taken a little bit more than the normal time. I would like to stop here, Mr.
Thank you,
Hello,
Prof.
sorry. I would like
Please, the question, please.
Hello, Prof.
We
Can I
talk about the large and small.
Please, Prof.
Please, one question, sir. Hello?
I'm with
Hello,
you.
Prof.
I'm with you. I'm with you.
Please, we talk about the large and small effect size. Is there any range to determine when it is small or large?
There is no, like the one I obtained here, there's no range, but it's obvious from what I have here that the effect, well, like in some cases, I think there are rule of thumb. There are rule of thumbs. I think you can search for that. I can't remember now.
Hello, Prof. Please, Prof. I want to find out why. Hello, sir.
Hello, please go on. Hello.
Yes, I want to find out why most times when you do a linear regression, and you see that most of your variables are not significant.
Most of your variables
are not significant. Are not significant.
Okay.
In the linear regression, most of the independent variables are not significant. What might likely be?
Is now, how do you choose your variables is very important. You could be guided by theory. You don't just bring all manner of variables into your regression. If you are doing, you should be guided by theory to choose your independent variable. For instance, if you are looking at high blood pressure, for instance, you might want to, theory or literature might have suggested age as a predisposing factor. Some other conditions must have been stated in literature. So you should be guided by theory, literature, experience, and a couple of other things. But not just that you sweep and gather all manner of variables and put as independent variable. Do I make sense?
Yes, but in my personal experience, even when I followed adopted a priori expectations and using literature on variables to use, most times economic variables, you still see most of the variables not being significant. Is it that there's a problem in the data, or there were things I could have done before doing the regression?
You don't have to flog your data if you have sufficient observations. If you have taking sufficient data points, and you have choosing variables based on experience, based on literature, based on theory, and you still have this, it means that's what the data is saying. So you don't flog the data to be significant simply because you want it to be significant. Is that okay?
Okay, Prof. Thank you, sir.
Yeah. Mr. Iredele, I think we have to stop. Are you there?
Hello, Prof.
Hello.
This when you run an OLS.
Yes.
Now, how do you know when the constant variance assumption has been violated for you to now go further to use the robust standard error?
Excellent. So that will be discussed next week because my colleague will now look at how to check for those classical assumptions.
Thank you, sir.
Yeah.